My pink ring has malfunctioned. The high voltage supply inside seems to be making loud crackling, popping noises. So recently, I took an interest in these little devices. Like this one is very good. This one is, I've been using it in my fridge and it does a great job of preventing different foods' odours from mixing. It keeps it sterile and also prolongs the life of food by killing bacteria and stuff. So the idea is that when you turn this on, a little blue light lights and it starts producing ozone. You can hear the ozone generator making a whistling noise, a slight whine. And that is producing a fairly strong smell of ozone. This one is based on the same style, and they're not just for fridges, they're for cupboards as well. And this one started off fine. It did make a slight whiff of ozone, but not very strong smell. But listen to what it's doing now. If I turn it on, and I find where the output is, it's not really supposed to be making that noise. And there's not much of a smell of ozone coming from it, so I think it's time to explore what has happened. So they've got a metal mesh around here, which is part of the problem, and it's surrounding this rim in the middle. So the only way I can see to get this apart, there's no screws hidden. It looks as though it's in two halves, but I'm guessing there may be screws hidden under here, so I'm going to have to get a screwdriver in. I've suddenly realised my screwdriver is not through here. That's awkward. I shall use a knife. This is ill-advised. I shall use the maker knife, and I shall prise under here. Oh, this is all going to end badly. Tell you what, I'm just going to pause and get the correct tool for the job. Not that there is a correct tool for the job. One moment. I have my screwdriver. Let us try and prise this out. And I don't think it's going to end very well. I will try prising it up. It might have been glued, or it might have been, I'm guessing it probably has been glued. I don't think it's going to go back in again. This is not. It's also chewing up my big pink ring. That's not good. I don't think this is going to come out in a dignified manner. It's going to be undignified. So let's just go for undignified by getting another screwdriver and just trying to push it right through this mesh. That's not working either. I may have to be super destructive here. That is super strong. How am I going to get this out? Have they glued it in? I shall have another prise. Although I'm chewing the edge up quite badly and keep turning it on, but it doesn't really matter. It is kind of coming out, but not really coming out. There it goes. Oh, I hate these meshes. What I'm seeing here is the classic ozone generator emitter and a selection of screws. Let us pop this open. The screwdriver is not fitting. Everything is going so well in this video. It's going so fantastically well. What about this screwdriver? Yes, that works. So the first problem I've got with this is the fact that this is using a very common ozone generator module, which uses a sharp point emitter under a metal ring, and it applies a high DC voltage between them, and it results in a corona discharge in the tip of the needle, and that's what creates the ozone. But there's supposed to be a means for airflow, because it creates what you could call, to name the sharper product image, an ionic breeze. It creates airflow, and that is needed to get the air to pass by the ozone generator. Let's see if this is going to open now. The pink ring is destroyed basically, so I'm not too bothered about doing any more damage. Okay. Lithium battery with protection, smaller circuit board than I expected, the high voltage module, and then the bit that actually generates the corona discharge. Very common. Now, at this point of making this video, there is that pandemic running around the world, the coronavirus pandemic, and everybody's just banging products like this out. This one seems quite good quality from the connectors alone. I'm going to turn this on and see where is that cracking coming from. But they're just banging them out, and I've had a couple that have been not working too well. What is causing that to just... It sounds like something is not really... It's not generating the corona discharge, it's just arcing across. Is it between the wires? Let's fish the high voltage wires out. It's high voltage at relatively low current-ish. Let's separate them apart. Is it doing it now? It's still doing it. I wonder if it's just got a problem with the sharpness of the emitter or the vicinity of it. that it's just not quite clicking. Let me just scrub the tip of that and then do it again. Oh, now it's doing it. Now that I've just cleaned the tip, it's doing this sort of noise. Hold on. Let me just put this up to the microphone, you'll hear it. Hear the noise? Now it's working. So I wonder if it's just, I wonder if there's just, the tip had been contaminated in some way. It just wasn't quite getting the voltage up there to actually, you know, it wasn't actually causing that corona discharge, or it might be the spacing between the two. Yeah, it's really making a hiss when I put my screwdriver up to it. I wonder if there's a distance problem. It might be that spacing isn't correct. But either way, let me doodle something out for you. Let me turn this little high voltage emitter off, and I'll grab my notepad. Previous project. Ink that has come through from the previous project, but that's okay. So the way these work, they have a needle, a sharp point, and a ring in front of it, and they create a high voltage. Say this is negative, this is positive. Technically speaking, it could be AC, and because there's a very high potential difference, it causes ionization, and you get sort of a strong stream of ions, but they tend to go direct over to the positive, and it causes this corona discharge. And in doing so, the flow of electrons actually creates an air propulsion effect. So you get air passing through that and coming out the front. So the way they've actually made this, they've got a metal plate with that hole in it, and then they've got the metal spike pushed through a piece of plastic. I can show you this whole module. Let's unscrew this module and I'll show you it. The circuitry itself will probably be a Royer oscillator. It will be potted in resin. It is potted in resin. But we've got the plastic plate. There's, I'll zoom down this. That's a good idea. It's got the plastic plate with a metal spike poked through it. The metal spike is going up towards this metal plate, which is the opposite potential, and it's got a hole through it. And the diameter of the hole and the spacing will be what affects that. But the whole point of these things is that when you mount this, if this is the arrangement here with the plastic plate, the pillars coming up and the little welded rivets, which they don't look like they're actually welded in this one. Oh, they are. It's kind of friction fit. I don't know if they've actually been sticked properly. But the idea is that you should have airflow coming in like that. It should have a means for the air to flow through it. But in this case, because of the design, they've got this recess down into this channel down here. There's no airflow place in. And then they've got a metal mesh in front, and it just completely defeats the actual concept of this. They've designed it so that it completely blocks any means of airflow into it. It's very strange. I mean, air will get in through the sides there, but not a huge amount. Very strange how they've done that. But it's kind of working now, I guess, now that I've scrubbed the tip a little bit, but I think that is on borderline of operation. Yeah. And also these leads, you have to take caution to keep these as separate as possible because of the... if it's high frequency, in this case, it's probably going through a voltage multiplier and it's probably DC. I shouldn't be fingering this. I don't know if it's got a charge or not. But you should try and keep them separate because if you put them too close together, if there is any AC or capacitive couple across, if it is DC, you've still got a decent potential difference between them. And it's always better to route cables like this, high voltage cables, a good distance apart. So I don't really know. I'm going to try nudging this. I'm going to try clean the tip and take a close look and see what went wrong. But it looks as though it's recoverable. But anyway, let's get this circuit board out as well and see what's in this. I'm guessing a microcontroller. I'm guessing a little MOSFET to switch that module. And I'm guessing a charge circuit. Okay, I shall unplug these. They've got two identical connectors. This is not good. Is it marked? Yes, it is marked. It's marked battery. That's good. And this one is marked. What is it marked? Oz. Okay, it's marked ozone. Right, tell you what, I'm going to take a wee picture of this and we'll take a look and we'll sort of reverse engineer it and see how it works. It should be straightforward. I can see there's the battery control chip, there's a microcontroller, there's a transistor that's switching the output. It shouldn't be too complicated. One moment, please. It has been reverse engineered. Let us explore it. It's a very simple, uncluttered circuit board, and in the back, there's just one track that actually bridges from the negative of the USB connector over to the negative side at this, but they are linked by a track. However, it does duck in, and just one plated through-hole comes on to provide the negative connection to the microcontroller. The microcontroller actually has the same pin out as a PIC12 microcontroller. We've got the incoming USB supply goes to the charger, which is a TP4054 type charger. It's marked 54BO. It is a 3K resistor. I could actually show you the schematic. Let's just point out the components. USB connector, dual color LED, microcontroller, charging chip, push button, and a transistor to switch the ozone generator. Battery connections here, ozone generator there, and this little resistor here that looks as though it may have been an option for fine-tuning the output of the ozone generator. Or maybe it's a fuse or something, but I don't really know. I would have thought that the protection of the battery would act as the fuse. But anyway, let's bring in the schematic. Here is the schematic. I shall zoom down on it, and then I'll try and remember to zoom back out again afterwards. The USB comes in, and there's a decoupling capacitor across it, lots of decoupling capacitors, and then it goes to the TP4054. Very similar to the triangular ozone generator in that it has a potential divider on the USB input side, 10K, 20K, and it goes over to the microcontroller, one of the input pins, and that tells it when it's plugged in to charge, and presumably at that point it cuts the power off. I didn't try that. And everything's pulled apart at the moment, so I'm guessing it probably does disable the unit when it's charging. I'm not sure why they do that. The charge current is set by this resistor here, 3K. There's a decoupling capacitor across the output. There's the battery, which does have, I'll just write lithium there. I'll just actually use a decent pen. Lithium. That's protected. It's got a little protection circuit in the negative. That is actually on the battery itself. It's the typical DW1 and MOSFET type arrangement with a resistor and capacitor. The microcontroller then has a very close decoupling capacitor. They've really gone by the book here. It has one button just pulling a pin to the 0 volt rail, and it's got the two LEDs in the same package, red and blue, with a 1K resistance series with each, and it's very odd. When it's in use, you push the button, the blue light lights, and then it starts flashing after a while, but really fast, really quite almost annoying. You open the fridge and it's like a little disco light show. But when the battery is running down, it gets worse because the red one also starts flashing really fast, but not at the same time. They have their own completely separate timers, and it just results in a very odd effect. To control the ozone module, which I've traced, the power is switched via a 1K resistor turning on a standard NPN transistor. The ozone generator only draws 30 milliamps, and it's just a Y1 NPN transistor. So as soon as that, that output goes positive, that will turn on, and the ozone generator will be active, and it will generate the whiff of ozone that is used. Let's point out some components on the board then that are worthy of note. Decoupling capacitor, decoupling capacitor, decoupling capacitor. Things worthy of note here, that's really about it. There's the 1K resistor going over to this transistor to switch the ozone generator here. And those are the two resistors for the LED. That's fundamentally it. There's really not much to it. It's very much a textbook design. Let's zoom back out again and take a look at the little ozone generator. I found the factor that makes it. I've also found out why this unit may have been so fickle. The factor that makes it is called Guangzhou Jingyong Household Electrical Appliances Co Limited. They could just give it a small catchy name, couldn't they? And this is called the Universal Mini Ozone Generator. This one is JYC-J5R1. This one here is the JYC-J5M1. This one's 5 volt. That one is 12 volt. And it describes it as carrier purifier, household air purifier, and desktop purifier. It's just for localized ozone creation. I would tame this down, but I won't bother taming it down because it should be fine. I'm just going to read out part of the text here. This was translated from Chinese. I get the feeling it may have been translated to Chinese from English because it's translated back quite well. It says, with the development of the ozone generator industry, there have been many controversies about ozone. Some say yes, and some worry about whether it will have side effects in the human body. So what about the ozone generator? The current home computer is a must-have for the family. The computer will inevitably produce radiation during use. This sounds like old computers. This radiation is harmful to the human body, but people still use it. Why? It is because this kind of hazard does not reach the level of prohibition of use. There are two factors in everything. The home ozone machine is the same. High concentrations of ozone do harm the human body, but the amount of ozone produced by the home ozone disinfection machine, wall-mounted air disinfection machine, is far from harming people. As long as it is used correctly, there is almost no harm to the human body. They've covered themselves by saying almost, on the contrary, the advantages of household sterilizers are very numerous and the uses are very wide. And it also has little disclaimer bits. Kill germs and prevent infection. Ozone generator sterilization is spectral, and conventional viruses can be killed. Conventional, I guess maybe COVID might be non-conventional, but it probably does kill COVID actually. Take care of family health. As a disinfectant is mainly used for tap water, mineral water, beverage water, swimming pool water, hospital sewage sterilization, deodorisation and deodorisation. Air purification in public sound stations, not sure what that is. Preservation of fruits, vegetables and eggs. And it goes on with a whole list of things that can be used. They're trying to justify this. Now, let me show you what happens when you run this at its intended voltage, because it is a 5-volt unit. I wonder if the reason that many of these little units are playing up is because they're running it from a lithium cell, which is about 4.2 volts. So if I turn this on, it's drawing 30 milliamps, and I'll let you hear it now. I'm hoping this is the correct microphone. And you can hear a healthy hiss, and I'm just getting the slightest whiff. Just trace level of ozone off that. I would say that it might be viable just buying these things just purely for the ozone module itself, but I get the feeling that if you could find a source of it, then these ozone modules would be quite affordable in their own right. I'm just suddenly remembering, what brand is this one? It doesn't say what brand it is. I guess there's quite a lot of companies make them. This is the ceramic plate one. It produces far too much ozone when it's connected to 12 volts. But this is kind of useful, this little dinky one, because it does produce that trace level. It's just a shame that the designers of this case, the circuitry seems okay. It's just the voltage they're using is just a bit too low. It's almost like it would have been better if it had been a 5-volt powered one instead. Particularly given it's already got that connector there. They could pretty much make one, but I would say that they need an air channel in for the airflow into this so it can actually create that turbulence. And this mesh is just really disruptive to the airflow. It's kind of attenuating its function quite a bit. But there we go. I may put it back together now, or I may just keep it for this little module, which I quite like. It's very simple. But that is the pink donut ozone generating air freshener for fridges, cupboards, and other small spaces that you might get a little minging smell, like, say, for instance, mold, or just that sort of mustiness, or the mixing of smells in fridges. It's reasonable enough. Terrible design. Modules absolutely fine. Circuit boards fine. Very strange mix. A little update already. I have made a modification. I decided, well, why don't we run this at full 5 volts? But that would require it being plugged into something like a USB power supply. So I modified the circuitry. It's also worth mentioning that there is something I missed. I didn't spot that there was a little sneaky track going under here and going up to that chip. And that was to tell it when it's actually in the charging status. So when you plug it into charge, it will flash the red LED to show it's charging until it's charged, and then the LED will stop. That's just a little indication line between the charging chip and the microcontroller. But I've removed the charging chip now from the circuit board. I used the hot air gun, a little bit of flux, and removed it. That's it there. It's tiny, isn't it? Really, really minute. But that is the charging chip that limits current sort of by using linear regulation, like a little resistor, but active. But I also removed this resistor here. So this is gone, and that resistor there is gone. And that was the bit that tells it that it's plugged in and disables the processor. So now I have removed that. I've removed that. And I put a wire link from here, the positive incoming supply, and I linked over to the battery positive. And now the unit will run when you plug a USB power supply into it. The battery is not in. I used the isopropyl alcohol technique in that. That worked a treat in that double-sided pad. It was really good. So if I plug it in now, you'll see that it flashes both LEDs briefly. Just a brief flash. And then when you press the button, it's just going to run purely off this battery pack now. And yeah, you'll hear it's quite spicy now. It's actually quite high output. And you might say, well, you can't use that in the fridge now, can you? Because you can't put lithium batteries in the fridge. Well, this lithium battery is in the fridge. In reality, the lithium batteries can be discharged at low current at low temperatures, and in the fridge, not the freezer. In the fridge, as long as you don't go below, well, I was going to say as long as you don't go below 0 degrees Celsius. Typically, a fridge will be in the region of 5 degrees Celsius. But the biggest risk with these batteries, standard consumer lithium batteries, is charging them at super low voltage. I'm just going to brighten this image up. That did not brighten up. Not to worry. But that's because this pink thing was on it. That should brighten up. There we go. But if you charge a lithium cell, a consumer-grade lithium cell at 0 degrees Celsius or below, it can actually cause metallic lithium to electroplate onto this sort of the negative electrode in it. But when you're discharging it, it's not such an issue, but you can't use it at the super extremes of temperature. It's not recommended to use it at its full current capability, discharge capability. But that's it. The modification has been done. The unit is now operating at the spicier 5 volts, which is better than the 4.2 down to 3 volts that it was operating at before. And it has a new lease of life. And it'll be interesting to see how even a simple 18650 based pack like this lasts in the fridge just on its standby current. So we'll see how that goes. I'm going to give that a test.